Okay, so we're still doing rotations, and this is the second part of the lesson from 4.3. Before we get into this, we should review what the rules were for rotations and the various angles that you need. So if we rotate 90 degrees counterclockwise, the rule for that was negative y x. If we rotate 180 degrees, the rule for that was negative x, negative y. And if we rotate 270 degrees counterclockwise, the rule for that was y, negative x. So what we're mostly focusing on today are compositions, more than one transformation. We're going to be rotating and doing something else, or doing something else and then rotating. So it's good to have these rules handy for when we need it. Let's look at example 1. In example 1, we're supposed to graph RS. The endpoints are 1, negative 3, and 2, negative 6. Let's go ahead and graph that right now. So 1, negative 3 is over here, and 2, negative 6 is over here. This is R, and this is S. We are applying this composition to it. We're supposed to rotate it first 180 degrees around the origin, and then reflect it in the y-axis. So we have to do these transformations in order. We're going to rotate 180 degrees about the origin. So we're going to use this rule on it. So the rule is negative x, negative y. We change the sign on the x's and change the sign on the y's. So for r prime, r was originally at 1, negative 3. R prime would be at negative 1, positive 3. We'll switch the sign on the x's and on the y's. Same thing for s prime. We apply negative x and negative y to it. We switch the sign on the x and switch the sign on the y. We get negative 2, 6. Okay. So that's where r prime and s prime are at after we rotate it 180 degrees. R and s 180 degrees. Let's graph that before we move on. So negative 1, 3 and negative 2, 6. This is r prime and s prime. You can kind of see that this rs is turned 90, then 180 degrees that way. So that's kind of how you want to check to make sure if you did the correct rotation and applied the rule correctly. Now we have to take r prime and s prime and reflect it across the y-axis. So here's the y-axis. And we just need to flip it over this line. I mean, this line is supposed to act like a mirror, and we just reflect it over. So r prime is at negative 1, 3. It is 1 away from the line of symmetry, or the reflection line. So on the opposite side, 1 away, should be r double prime. And s prime is actually 2 units away from that reflection line. So s prime would be 2 units away there. So the final result, we rotated RS 180 degrees, so we turned it that way, or sorry, this way, counterclockwise. Turned it here, and then we flipped it over the y-axis. So your final result, r prime was at 1, 3, and s double prime is at 2, 6. So I want you guys to do the same thing for number 2. Graph R and S, but this time we're going to switch the order. I'm going to ask you to do the reflection first, and then rotate it 90 degrees around the origin. Okay. So hopefully you guys did this. You graphed R and S first. R is at 4, -2. S is at 3, -5. We're supposed to reflect it over the x-axis first. So that's across this line. So R is 2 units away from the axis, so 2 units above would be R prime. S is 5 units below, so 5 units above would be S prime. So to have R prime and S prime handy, the R prime is 4, 2, S prime is 3, 5. Now we need to apply the rotation. We're going to rotate it around the origin at 90 degrees. So the rule for a 90-degree rotation is -y x. In normal words, that's take your y value, change the sign and place it first, and then put your x value second. So this means R double prime, if I took the y value and changed the sign, that's -2, and I write that first. Take the x value and write that second. S double prime, take the y value, write that first with the sign change, take that x value, write it second. So the coordinates on R double prime and S double prime are -2, 4, and -5, 3. So this is R double prime and S double prime. So you can kind of see I took this shape, this line segment right here, and turned it 90 degrees counterclockwise. So in example 3, we're asked to do another composition. This time it doesn't involve reflection, it involves a translation, a moving. It does also still involve a rotation. So let's go ahead and graph AB first. -4, 4 is right there. -1, 7 is right here. So that's A, B. So I have a graph. I'm going to apply the translation first. Now the rule for the translation is x minus 2, y minus 1. Remember that x minus 2 means you take all the x values and subtract 2 from it. X minus or y minus 1 means take all the y values and subtract 1 from it. So A prime, -4 minus 2 gives me -6. 4 minus 1 gives me 3. So A prime is at -6, 3. B prime is at, starting off with -1 minus 2 is -3. 7 minus 1 is 6. Let's go ahead and graph that before we apply the rotation. So -6, 3 and -3, 6. This is A prime and B prime. So it looks like we just moved the line segment 2 units to the left and down 1, which is the exact thing what that translation wanted us to do. And now we have to rotate the primes. So we need the rule for rotating 270 degrees counterclockwise is y -x. In words, it means take your y value, write it first. Take your x value, write it second, and then change the sign on it. So A double prime, I'm going to take the y value, write it first. I'm going to take the x value, write it next, but change the sign. So A double prime is 3, 6. B double prime. So again, take the y value, write it first. Take the x value, write it second, and then make it an opposite sign. So 270 degrees counterclockwise would end up being somewhere right here. So 3, 6 is my A double prime. 6, 3 is my B double prime. I want you guys to go ahead and try number 4. Graph that triangle and then apply these 2 separate transformations on it. Rotate it 180 degrees around the origin and then translate it using the rule x plus 4, y plus 2. Let's go ahead and graph this triangle first. 1, 2, 3, 5, 6, 3. So this is T, U, and V. Okay, so the first thing we were asked to do with this triangle was rotate it 180 degrees around the origin. So we need to remember the rule for rotating 180 degrees is negative x, negative y. We just change the signs on our x and our y. So T prime would be just negative 1, negative 2. U prime would be negative 3, negative 5. V prime would be negative 6, negative 3. Let's go ahead and graph that. So this is T prime, U prime, V prime. So afterwards, we need to apply this rule to it. We need to take x, add 4, and y, and add 2 to it. So T double prime, if I add negative 1 plus 4, that should get me positive 3. If I do negative 2 plus 2, that's 0. U double prime, negative 3 plus 4 is 1. Negative 5 plus 2 is negative 3. And V double prime, negative 6 plus 4 is negative 2. Negative 3 plus 2 is negative 1. Let's go ahead and graph where that final result would be. 3 zeros here. 1, negative 3 is here. Negative 2, 1 is over here. So this is T double prime, U double prime, and V double prime there. So this is our final answer after all the transformations. You guys may remember a couple days ago we talked about line symmetry. If a shape has symmetry, a line of symmetry where you can just draw it down and it'll reflect one part of the shape to the other. We're going to talk today about rotational symmetry. If we can turn a shape and it will be the same original shape from before. So a figure has rotational symmetry if you are able to turn it at 180 degrees or less, and it will have kind of the same shape you started off with. So if you look at this pinwheel, here's it at the original, here's it after a 45-degree turn. It doesn't look like the way it started, so it doesn't have rotational symmetry for 45 degrees. But if I rotate it 90 degrees, it looks the exact same thing as if I started. So it has rotational symmetry of 90 degrees. And again, if I rotate it all the way to 180, it has rotational symmetry for 180 degrees. We're mostly just interested into like the smallest number of degrees it has rotational symmetry for. The reason the limit is on 180 is because if you go beyond that, the only other number that you'd have rotational symmetry for is 360, which means like a full circle turn. Of course, everything has a rotational symmetry of 360 degrees. Because if you rotated something a full circle, it's back to where it started. So in these pictures, we have to decide if the picture has rotational symmetry or not, and figure out how many degrees that would be. So this parallelogram, we just see if it has rotational symmetry. So keep this picture in mind as I turn my paper. It's pointing, kind of going this way, has a positive slope, it's kind of pointing to the right. And if I just keep turning and see if I end up with the same shape. No, that's not the same shape. No, well, that is the same shape. So I got the same shape once, and back to normal, kind of twice. So it does have rotational symmetry. And the way you figure out the degree, the angle of rotational symmetry, is you take 360 degrees, a full circle, and divide it by how many times you could rotate it, and it would end up being the same picture. You're allowed to count like the final thing. So let's do this again. This is one time it was the same, and now two times it's the same. You're allowed to count that last time. So 360 divided by 2 is 180 degrees. So it has 180 degrees rotational symmetry. So let's look at this octagon and see how many degrees it may have. It may not have any. So it kind of looks like that, a stop sign. That doesn't look like a stop sign yet. So that does. So that's one turn, two turns, three turns, four turns, five turns, six turns, seven turns, and then 8 gets us back to where we started. So this definitely has rotational symmetry. We could have turned it 8 times out of 360. So if we take 360 divide by 8, that'll give us the degree, the angle of rotation. And that's 45 degrees. So this has a rotational symmetry of 45 degrees. This trapezoid, let's see, how many turns will it take to get the same? So, this is not the same. That's still not the same. It's only the same when I'd go a full 360. So that's not allowed. So this one doesn't have any rotational symmetry. So I want you guys to look at the next 3 shapes and find out if it has rotational symmetry or not, and then how many degrees it would be. This rhombus, that's the same, that's not the same, that's the same, that's not the same. So I could rotate this twice. So yes, so 360 divided by 2 is 180 degrees rotational symmetry. This shuriken or ninja star, so that's the same once, 2 times, 3 times, and finally 4 times. So yes, and it's 4 turns, so it has 90 degree rotational symmetry. This triangle, nope, that's not the same, nope, that's not the same, nope. So it only is the same after 360 degrees. That doesn't count, so no rotational symmetry.